here's another group of problems in which series appear, and it is again solving differential equations, but not the ordinary differential equations as the previous one I mentioned, but what we call the partial differential equations, which which we should find the function of several variables. Here u is a function, we should find u, and u is a function of two variables x and y. This is the derivative of the second derivative of u with respect to x, and this is the second derivative of u with respect to y. And also you should satisfy these conditions. U should be 0 when x is 0, u should be 0 when x is pi, u should be 0 when y is infinity, and u should be x cubed when y equals to 0. The several variable functions and the calculus of them, they usually don't teach that in an elementary calculus courses. But you probably learn that in some other courses, okay? So, and this is a problem of heat transfer. And sometimes we need to know about the heat transfer. For instance, suppose we want to manufacture an engine of a car or of a motorcycle. But when the engine burns the fuel, that the heat produced by the burning do some work for the engine, okay? But it also produces an extra heat, which could be harmful for the engine's function and the engine's structure. So we want the extra heat to take out. This is an example of heat transfer problems. Okay, let's solve this equation and see how the series appear. And u here is temperature. Okay, let's solve it. Here, let's suppose that u be a function like this, e to the alpha y plus beta x. Okay, let's see if this satisfies this relation. This would be let's calculate it. The derivative of the second derivative of u with respect to x. Let's first calculate the first derivative of this with respect to x, and this is, let's show that by u prime x, and this is beta e to the alpha y plus beta x, and the second derivative would be beta squared times this. Okay, again, the derivative in the several variable functions, you learn that in the several variable calculus courses. Okay, so this would be this beta squared into this, let's not write it again, plus, and this would be alpha squared e to the alpha y plus beta x. So which is beta squared plus alpha squared times e to the alpha y plus beta x. Now, and this is equal to 0, so e to this could not be 0 because e is a non-zero constant, and to any power is not 0, so this should be 0. Beta squared plus alpha squared is 0, then beta and alpha are both 0. So here then u would be e to the 0 or 1, but u is equals to 1 is not a solution because u should be 0 for x equals to 0, but here u equals to 1, but we don't give up here. This equation here in real numbers, beta and alpha should be 0, but how about in imaginary numbers? And you may be familiar already with the imaginary numbers. Are the numbers containing the square root of -1, which is not a real number. Okay, and we show that by I equals to the square root of -1, so I squared would be -1. Okay, and let's here write it as this plus as minus I squared. This is alpha minus I squared. Okay, I squared is -1, minus -1 is plus. Plus 1 would be original thing. Okay, so this is equal to beta minus I alpha squared, beta squared minus this, and this is beta minus I alpha times beta plus I alpha. Is 0, then from here beta equals to I alpha, and from here equals to minus I alpha. So here let's plug them into beta. this would be plus and minus I alpha. This, this function satisfying this relation, but how about these conditions? But before that, this is as I mentioned, U is a temperature, but from here U is an imaginary number, so this is nonsense. How could an imaginary number represent a temperature? So this here I missed X. Okay, so we could prove it by considering that this is a linear function. Sorry, this is a linear equation. And what does that mean? That means that if U1 and U2 be two solutions of this equation, then any linear combinations of these two are again a solution of this. You could check that. This is easy. Again, this is a linear combination of these two, is a solution of this. So here we already got two solutions. This is not a one function, this is two functions. One is e to the alpha y plus I alpha x, and the next one is e to the alpha y minus I alpha x. So the difference of them over 2i which is a linear combination of these two is also a solution of this equation. According to the to the laws of imaginary number, this is equal to e to the alpha y times sine alpha x. If you're not familiar with this, don't worry,